Good afternoon, everyone. I'm a research scientist at Orion Space Solutions, and today I'll be sharing our perspective on the utility of RO data and additionally commercial RO data on ionospheric data assimilation. The guiding question of this talk is the impact of RO data specifically on bulk global electron density, so I won't be going into scintillation. And this is a talk in two parts. In part one, I actually won't be touching on commercial RO data. Instead, we'll be looking at Cosmic 2 Formosat 7 data and how it stacks up relative to other common ionospheric observation types, ground GNSS TEC, and ionosons. We'll be looking at three different parameters of interest. One is the VTEC, the second one is FOF2, which is the plasma frequency associated with the peak electron density of the ionospheric F2 layer. And the third one is HMF2, which is the height at which that layer occurs. And in part two, we'll bring in RO data from a commercial provider as well. And for the sake of time, we'll just look at FOF2. The way we're studying these two different parts is through OSSIs, or Observing System Simulation Experiments. We've heard about these a few times, so I'll be brief. Basically, we have a truth model or a nature run. We use that to synthesize the measurements of interest, and then we put those into the data assimilation model. We get an analysis, and then we can compare that back to the truth. And OSSIs are great because you can do that comparison at all places and all times. So here it's showing FOF2, but of course the model is three-dimensional and time-varying electron density. So OSSIs are great for answering what-if questions, like what if you change your observing system, which is what we're looking at in this talk, or other things like what if you change your data assimilation or the algorithms within it, or the error models on your data. So at Orion, we have an internal OSSI tool called the OSSI tool, or OSSIT, but of course there are community tools that can be used for OSSIs, such as NCAR Dart with TiGCM. Part one, the impact of RO data. So we'll be talking about the relative merits of three common ionospheric data types that are used in assimilation. First is ionosons, which is ground-based HF radar, can give you information about the bottom side electron density profile. And then there's two different versions of TEC. So we're familiar with radio occultation geometry. You can get TEC along that GNSS to LEO satellite link. You can also get TEC from GNSS ground stations. So to build a little bit of intuition, let's consider some differences between GNSS on the ground measuring TEC and radio occultation measuring TEC. So in this simplified example, let's assume that ground GNSS TEC has vertical ray paths. Of course, in reality, they can measure at different elevation angles. So if we imagine an ionosphere that's just two layers, we have higher density in red on the top, lower density on the bottom. These two different ground stations would measure the same TEC. However, if there is a horizontal structure, it would be sensitive to that. On the other hand, with radio occultation, it is not sensitive to the horizontal gradient if you assume completely horizontal ray paths, but it is sensitive to a vertical gradient. So there's a couple of questions we're going to answer. First, does RO help specify vertical structure? Our intuition says yes. Second, does ground GNSS TEC help specify horizontal structure? Again, our intuition says yes. And the third and most interesting question is, does the combination of those two measurement types specify the ionosphere better than either of them in isolation? So here's our process for doing that. We start with the truth model or the nature run using something called the noisy truth model, basically TiGCM plus some smaller scale structure. And then we're going to do 11 different data assimilation runs with unique combinations of our three data types. So that's ionosons, that's ground GNSS, which we try assimilating in both a relative and absolute TEC sense. And the third is radio occultation, which is assimilated, in this case, in a relative sense. So then we compare the performance between these 11 runs, as well as the background model, which is IRI, and see how it shakes out. So a little more detail on our data. So particularly for radio occultation, you have measurements along this ray path, which actually spans 1,000 or more kilometers horizontal difference through the bulk of electrons in the ionosphere. So the way we visualize it is with these so-called fan plots. So all the colored splotches you see on the bottom show the extent of the ray path through that 1 to 500 kilometer altitude region of interest. And then in the bottom right, you can see ground GNSS, which also has some extent away from the ground station location, as well as ionosons, which are a vertical instance. Those are the green triangles. Our simulator is an internal one we call Mazda, which is a re-architected and upgraded version of IDA 4D for those familiar with that. And then there's some other details here I'll glaze over. Here's a snapshot of the vertical TEC errors. So this is just at a certain time step. And you can see that the errors are reduced for certain runs. For example, in the bottom right, you see the RO and absolute ground TEC run has greatly reduced errors in the vertical TEC. So this is just to build understanding for the general summary figure I'm going to show. So the earlier figure was the errors in VTech at one place, at all places at one time. So if we combine it into a histogram for the entire 24-hour assimilation run, all places, all times, this is what it looks like. So the top is the background, the IRI model, and the bottom is the VTech error for that one particular assimilation run. So now here's everything together across our 3 metrics of interest and for the background and 11 assimilation runs. So each of the shapes you see on this plot is the histogram just rotated by 90 degrees. A note about the Ionospheric data, there isn't that much available globally, so it didn't cause that much of a difference in these global metrics. So each of these parts on the plot is actually 2 stacked histograms, one without and one with Ionospheric data, and there are only slight differences between them. So we're going to focus mainly on the relative merits of the ground GNSS and the radial occultation data. And this analysis is also limited to equator word of 40 degrees since we're only looking at cosmic 2. So on the top panel, we see that absolute ground tech helps specify VTech in those rightmost 2 histograms. You can see that they've gotten a lot closer to 0 on average. In the middle panel for HMF2, we see that RO data helps specify it, although the effect isn't as dramatic. And for FOF2, we see that RO data also helps specify it. But interestingly, if you additionally include absolute ground tech, it makes things a little bit worse. And you can see that in the lower right histogram. Another takeaway is that relative ground tech does not add much to RO, at least in these assimilation runs. And then for absolute ground tech, it adds VTech performance to RO. But again, I'll point out that it takes away a small amount of performance in FOF2. So for our 3 questions, number 1, RO data does help with the proxy for vertical structure, so FOF2, HMF2 metrics. And for horizontal structure, which we're using VTech as a proxy, the ground GNSS tech does help improve that. And interestingly, for question 3, the combination of these measurement types does not necessarily improve performance on all 3 metrics simultaneously. So the main takeaway is that no combination of data is best for all 3 of these simple global metrics, but I will note that the inclusion of RO data has either a neutral or a very positive impact. So I would say that it should be included. And now, in the last couple of minutes, we'll look at the impact of commercial RO data now that we understand how those 3 ionospheric measurement types play against one another. So the second OSSI that I'm presenting on here was done as part of the US Air Force Commercial Weather Data Pilot Program. During that, we evaluated Planet IQ TEC data as well as neutral atmosphere, but that's not the topic here, for the NOMS 2 satellite. So for today, for this OSSI, we just took 1 day of the Planet IQ data, meaning just the NOMS 2 and GNSS satellite positions. This is an OSSI, so we synthesize the measurements. And you can see an example of 15 minutes of ionospheric coverage there. So here it's just 2 analyses instead of 11. Analysis 1 is the 3 common data types with just Cosmic 2 RO. And analysis 2 is all of that same data with the additional inclusion of Planet IQ. So I'm showing results just for the FOF2 specification part of the OSSI analysis. So we'll go through this stair-step plot here. So we start with the truth model. In this case, it's just standard TIE GCM. This is the nature run state at a certain instant in time. And then here's the background, IRI, and the 2 analyses. This is the one without commercial RO data from Planet IQ, and this is the one with commercial RO data. Going to the next column of the stair-step plot, we're looking at errors relative to the truth model. So you can see it there for the background, for analysis 1, and for analysis 2. Now in this 3rd column, we're looking at the improvement, which means the percentage point reduction in the error of analysis 1 relative to the background in this case. And I should mention that this is averaged over the entire day. And so here's the same thing for analysis 2. And then finally, for the last column of this plot, we look at the differences between those improvements, and this is what we're calling the value of commercial RO. So this is the additional reduction in error of the analysis relative to the background when you add commercial RO data. So the results here are unsurprising. This is Planet IQ NOMS 2. It's in a polar orbit, and there is no Cosmic 2 RO data at high latitudes. So we, of course, see a lot of improvement at high latitudes. The one exception is in Eastern Antarctica. And the reason for that is that the background model for FOF2 happened to already be pretty accurate. So we don't see that much improvement. But again, this is just one satellite for one day. So you could do these sorts of OSSEs across multiple days with any sort of observing system you want to get more information like this. And so really the improvement comes down to the coverage of the commercial RO measurement. So we did a quick coverage analysis. Again, that RO ray path goes through thousands of kilometers horizontally in the ionosphere. So the way we assess coverage is by looking at all of the voxels in the ionosphere that are touched by that ray path. And so here are the OSSE results compared to coverage. So these top two plots are that coverage analysis, the voxel-based method I just described. In the top left is Cosmic 2, the 6 satellites, and the top right is when you add Planet IQ as well. So this is showing the mean visits per hour at the 300 to 310 kilometer altitude layer of the ionosphere, which is near HMF2 generally. So the bottom left plot is comparing those top two plots and showing the coverage improvement when you include commercial RO. So those light green parts near the poles, those are completely new coverage. We had nothing from Cosmic 2 before. And then the other colors are showing differing levels of percent increase in mean visits. So you can see that the coverage is improved most over the poles, as I mentioned, as well as at the local times of the Planet IQ NOMS 2 satellite orbit. So the takeaway is that areas with new or greater than 75% increase in coverage see significant FOF2 improvements. So this bottom right plot is that same value of commercial RO plot, except transformed into local time instead of longitude. So again, the results are unsurprising, but where you have coverage, you see improvements in FOF2. So for anyone who's interested in more information on part 1, my colleague Joe Hughes gave a much longer version of that talk at the Geospace Data Assimilation Working Group. And we have a paper in preparation on the same topic, but including more things like end user specific HF propagation impact. And we're seeing so far that RO data does help a lot with the landing location of an HF propagation ray. And for anyone interested in more info on part 2, we have a paper out on that. So here are some QR codes for the additional information. That's all I had, and happy to take any questions. Thank you.
We have time for one short question.
Hey, Ian, nice talk. Paul brings this up every once in a while for us. So I think that you were Cosmic 2 and radio occultation, you were using an absolute TEC measurement. What would happen if you would just use use a relative TEC?
So for these data assimilation runs, we assimilated all RO data in a relative sense. So yeah, any offsets wouldn't matter. But of course it is synthetic data. It's idealized without noise. So yeah. Thanks.
So we would like to invite the next speaker is Paul Strauss from Aerospace. It's invited talk.